Hello, this is Darren Pulsifer, Chief Solution Architect of Public Sector at Intel, and welcome to Embracing Digital Transformation, where we investigate effective change leveraging people, process, and technology. On today's episode, the science behind digital twins with special guest Rob Watts, Principal Architect of Intel SceneScape. Rob, welcome to the show.
Thanks, Darren. It's good to be here.
I'm glad you came. You're working on some really cool technology at Intel. I've seen it in action. It's super cool. I've seen it on stage in live demos. Super cool stuff. But we're going to tease everyone and say, you got to wait. You got to wait because we want to hear about Rob first. Tell my audience your background, and then we'll dive into why you're doing what you're doing.
Well, it's kind of, everybody has their story, but I come to things from more of a physics background rather than like your traditional IT background. So really, I have a master's in applied physics and did some work in, I did my, some graduate stuff at Los Alamos Lab. And then I went into semiconductors for about 5 years and then did some entrepreneurship and then landed at Intel. So focusing more on holistic solutions, not just one particular discipline. How do we bring together connectivity, wireless, IoT, sensing in order to do something really special?
Okay, well, so you're a physicist.
Well, I have a master's.
Well, that's what you learned in school.
Yeah, I did study physics or applied physics, and at the time it was a concentration in like microwave theory and applications of electrodynamics. And then,
don't get me started. That was my hardest class in college.
Yeah, it's
because I was electrical engineer going into the power option, and my hardest classes were my electromagnetic classes.
Yeah,
and you probably eat that for lunch. That's no big deal for you, right?
Yeah, you know how things go after not using something for a while, but the principles remain, right? Actually, one of the more challenging classes I took in grad school was plasma physics, which somehow managed to combine the hardest parts of quantum mechanics, fluid mechanics, and electrodynamics into one discipline. So yeah, that
sounds horrible.
I'd like to say I aced the class, but I'm not sure I did.
Oh, I was happy I passed my electromagnetics class with a C+.
Yeah.
I was like, that's a passing grade.
Yeah, exactly.
So, all right. So, Rob, tell me a little bit about how you got involved in what you're doing now, which is mostly around mimicking the real world in software. You're creating digital twins, basically, right?
Yeah. Well, it really comes down to what are we trying to do with sensor data, and coming at it from a physics perspective. How can you make the data as reusable and valuable as possible? And so what it comes down to it for me is, how do we get it in the right units, in standard units? So let me give you an example. In a typical AI application that uses video, what we do is we run it through a deep learning model that's running some inferencing that draws a little bounding box around a person or a dog or a vehicle or whatever.
Yeah, object detection, right?
Yeah,
basic object detection.
Detection draws a bounding box, or you could do fancier stuff like semantic segmentation that actually, connects the dots around the object, or like classification, which is saying what's in the whole image. But ultimately, the context for that detection is in the camera, right?
Right.
So the interesting thing is, when you're going to a manufacturing use case or healthcare or transportation, it's not enough to say, I detected something in the camera. If you don't know where the camera is, the data is essentially useless.
When you say you don't know where the camera is, you mean in the physical space, right?
In the physical world. If I don't know the pose of that camera, and I can't transpose the data from a bounding box into something that is in real world coordinates, the data doesn't really mean much.
Oh, interesting. I never thought of it that way. I thought, because the camera is really only taking a 2D picture,
Right.
right? Right. And the bounding box says, hey, I've got something in there. I could even say, I have Rob here. I could say that, right?
Yeah. What
But
is here?
yeah, where is here and what is here?
Yeah.
I guess that matters. Yeah.
So I guess the thing that we're trying to answer is three things: what, where, and when. What is it that we saw or detected? Where was it, and when was it? And time coordination and precision time stamping is pretty well understood. You can look up an NTP server and get a timestamp. But doing the same thing, if you have GPS, that's helpful. It gets you within a certain radius of where you think something is, but you don't always have it. It might be out, might be indoors or something like that. But you also don't get like a precise pose. You don't get like the actual direction the camera is pointing, or the object is pointing, shall we say. And if you have the camera and you have the exact pose of the camera, then that's some additional information that essentially what we're really trying to do is well, let me back up. If we do create like a digital twin, that's an overloaded term, but a digital twin or a mirror world of the real world, if we have a digital representation of that real world, the real question is, how do we project the sensor data onto that virtual world? So you follow
Okay,
what I
so
mean?
all right, I gotta dumb this down so
Okay.
I understand. Okay. So what you're saying is I've got cameras and sensors out there that are
Mhm.
taking pictures, are telling me
Right.
what's at their location. But that's meaningless if I can't superimpose that in the real world or a representation of the real world. Otherwise, I can't see the real interaction between those objects that I'm detecting
Mhm.
and the real world.
Yeah,
Is that
maybe we can think about it even a little simpler way. Is that in order to make sense of the sensor data, I need to know where the virtual representation of the sensor is. So I essentially
oh
need to
god, oh yeah,
digital
yeah,
twin
yeah.
the
Okay.
sensor.
Right. So like at my house, I'm gonna even dumb it down even more. At my house, I've got security cameras
Hmm.
because someone stole something off my porch, Amazon, someone
Yeah.
stole something. So all of a sudden the Ring camera was not enough. And I put up 5 more cameras
Right.
around my house. And I have them labeled, right? Front, side, back,
You know
whatever the
what that
case may
means?
be. I know what that means. But the computer doesn't know what that
Right.
means. It has no
Right.
concept of that.
Exactly right.
So myself, when I'm looking at all the cameras, I can see I saw this person walk through the front, come onto my side yard and into my backyard.
Hmm.
I know that because I know where I put the cameras and I name the camera front, side,
Yep.
and back.
Yep.
Right?
What if you don't speak English?
Yeah, that's bad. Right?
Right.
Or my computer, if I wanted my computer to watch my kids sneaking out of the house at night, I have 3 teenagers, right? Then I want to know which path they took.
Right.
The computer can't tell me that without having some notion of where those cameras are with respect to the house,
That is
right?
exactly right.
Got it. Okay. So, my kids, if you're watching this show, Rob's going to help me catch you. I'm just saying.
It's not the first time I've heard that.
Yeah. Okay. So why did you get in this space? I mean, why does it matter that why does it matter that the computer has an accurate or semi-accurate representation of the real world?
Well, it's really about data reuse. How do you represent the data in a way that more than just one application can make sense of it? So the idea is, like, if I put you know cameras up in a factory for monitoring where product is, or monitoring something about the space, like where people are for security purposes. Typically, you put up security cameras over here, and then you put up machine vision cameras over there. And those two systems, like one for tracking a product and another one for tracking people, don't talk to each other. They don't
They're completely
represent the
different
data. Yeah.
systems.
And another one would be like, I put up a security camera to monitor this entryway here, and I have an AGV that has cameras on it coming down a corridor. And then you you know you have a blind corner. One system knows that the person is about to be run over, but the other system doesn't know it. There is a digital version of something in a computer somewhere over here, and the robot can't talk to it. It doesn't know how to connect the dots. So the idea is that if you have this digital version that is essentially a common coordinate system for everything to work in, then the robot can slow down because it knows that the person is there, right?
It could. All right, I got you. So this commonality or this common way of describing the real world ends up being very important when especially in factories, right?
Yeah.
Factories where I've got safety systems, I've got security systems, I've got product quality,
Yeah.
all these things that are running. Wouldn't it be great if they could all share the same uh, virtual instance of the world? Is what you're
Yeah.
saying.
It's essentially trying to bring the spatial awareness into machine AI, right? It's like how to, if you think about how we as humans make sense of the world, we create this mental model of the space around us. It's in 3D. It's in 3D plus time, actually. And we use our senses, audio, touch, vision, in order to build that 3D understanding of the world around us. And then we can determine how to act. And really, I just don't see how we're going to drive forward machine-based AI without having that spatial understanding as one of the core fundamental components of that AI.
Gotcha. So I really like the premise of it. I think it's super cool. Um, could we leverage this also in the VR and AR world as well? Where, hey, maybe let's talk about Chernobyl, right? If I had an accurate model of Chernobyl and sensors currently, I could go in there with a VR headset and a robot and move around and work in that environment without going in the environment. Do you see that as one of the possibilities here?
Yeah, absolutely. It's this notion of being able to. Well, I like to say AR for when you're there, VR for when you're not. So
Okay, yeah, I
the
like that. Yeah.
the amazing thing about, I actually think about augmented reality and robotics as being closer together than augmented reality and virtual reality. Um, Augmented reality and robots, they have to operate within the physical space. They need to be
Yeah,
able to
VR
capture.
doesn't,
Right,
right?
right. But you
That
can
makes sense.
use the data that is captured from the live scene to create that digital twin of the physical space to mirror the physical space that you could walk through in virtual reality when you're not there. So there's this sort of continuum that happens when you're in the space. But then if you can store and maintain the history of that over time, and maybe push up the data in near real time, you could ultimately walk through your factory, walk through Chernobyl, walk through that area where humans can't particularly go for one reason or another, as if you were there in virtual reality. And ironically, the virtual reality headset is creating a digital twin of the space you're in
Yes,
that you
it
could
is.
in
Yeah,
turn
it is. It
go
is.
somewhere else and then walk through when. So it all comes together. So I need to sort of map and twin the space where I'm operating in both cases, when I'm remote and when am on-prem or in the physical scene.
So you've really taken your physics degree kind of to the next level, right? Applied physics, right? Because now you're saying, I understand the physical world. You understand, our understanding of physics in the
Mm-hmm.
physical world. And now you're saying, let's see if we can capture that in the virtual world,
Yeah.
in a twin of the real world. What other use cases do you see that we can use with this kind of technology? Is it just it's super cool, but obviously, I mean, what other things can I use for this type of technology?
Well, I would say that there are use cases out there right now that we use every day that you don't quite realize. But some things are more emergent, like autonomous driving. They need to work against a more real-time digital twin. But every time you use Google Maps, for example, you're using a digital twin. You're using a
Oh, you're right,
representation
because
of
it tells me traffic,
yeah.
right?
Yep.
It tells me accidents and
Exactly.
all right. So people are already using digital
That's
twin
right.
already.
They just don't necessarily call it that. So there's a few things that you really want to think about. Is one of them is like the latency aspect of it. The Google Earth, for example, is a highly latent digital twin of the world. You know that they probably
Yeah,
flew
go
the
look at the
satellites over
front
a
of your
long time.
house,
Yeah,
right? If
exactly.
you look at the front of your house,
Right.
it's not the same cars that you had
Yeah,
a year ago or whatever. It's someone was visiting that day. You're no longer friends with them.
yeah,
And you're like, what is their car doing in front of my house,
right.
right?
And that's it. Or I cut that tree down, and I forgot we had that tree there.
Yeah,
So it's sort of a historical thing. But imagine if we can reduce that latency and get to the point where you're near real time. Now we can start enabling closed loop type controls, and maybe the implementation of that is running closer to the scene itself. And I like to think that maybe in the future we'll actually have the truly intelligent scenes, like in that Iron Man movie, like with Jarvis. It's like he's in the
Oh
house.
yeah.
It's like you can talk to him. He knows where everything is. He knows where the robots are. Knows who's there. You can say, "Hey," you can imagine the situation where you can monitor where you are, and the lights are just kind of following you, and whatever. You know, that real time
See,
closed loop control aspect of it is coming
okay, so Rob, have you already set this up in your house?
to some extent. My
Yeah.
it's so funny because
you're a true applied physicist right
yeah,
there.
it's funny. One of our lead developers, Chris, he has it set up at his house, and so he can monitor, when there's a delivery truck versus not a delivery truck, or when the mail arrived or whatever. And he has this notification being sent to his phone, and it gives a certain alert when it's the UPS truck or whatever, the Amazon truck, versus when it's something else. And his dog has learned which sound it is. So it's a video of this. Is
Okay,
hilarious.
there it is. My
Yeah,
dog uses
right,
SceneScape. My dog uses a digital twin.
right.
I love it. That's a headline.
So it's like Pavlov,
That's
it's
gonna
like
make the papers.
he learned that it's a certain sound, so it's doing the dog's job for it. So I think that's just hilarious.
That's awesome. So, factories, big, huge use cases in
Mhm.
factories, security, inventory management, all that. Have you
Retail, yeah.
retail? Yeah. Can I? I mean, Amazon is using it. Are they using something similar to this in their no? What are they? Their no touch
Like
stores or
Amazon
their
Go.
like
Yeah,
Amazon Go? Yeah. Are they
yeah,
using this kind of technology?
absolutely. I think any case where you're having multiple sensors coming together to try to track where objects and people are and everything using different modalities, I don't know of any other way to do it. You really need to calibrate all of these sensors together into the same coordinate system. And if you were to introduce that sort of common representation or digital twin or whatever we want to call it, that is a fundamental way to do it. Really, it's just getting it into SI units, and think back to the physics thing. It's like, how do I get it from pixels into meters, or from pixels into geospatial? Those sorts of, like, thinking about the units first principles is really a good way to go, I think.
That reminds me, and you probably know the story better than I do. There was a probe that we sent to Mars that had the wrong units, right? It was feet
Rather than
over
meters.
meters or something
Yeah,
like that.
yeah.
And because they weren't in a standardized set, what happened? We crashed it right into the ground.
Yeah, we just lost
Well,
it.
yeah, right into the Mars ground, I should say, right?
Right. And it's because we had people from Europe working with people from America, and there's just this assumption that, of the unit.
So it's even worse in the computer industry, right? As far as the different types of data that's collected and the non conformity to any kind of spatial units or whatever the case may be.
Well, I guess it depends on the discipline, right? But like with an IoT and like the type of sensor data that comes off of IoT, or even things like temperature and humidity, those sorts of things have some things are more mature in terms of the standardization around it, or there's a standard in one industry that's different than a standard in another industry.
Yeah, exactly. Yeah.
So the real idea is to focus on how do I get to SI units and represent it there, but also look outside of your industry. Like for example, when you're creating a digital twin, so called, maybe there is another industry that's already done this. And an example would be scene graphs for gaming or rendering. They already have a representation for a physical space or a virtual space. And if we just say, oh, this is just a way to transport the data like GLTF or Universal Scene Description Format, USD, there is a way to transport that data that's standards based. So let's just adopt that and maybe extend.
So, and is that what you guys did? Because this sounds kind of funny. Because I know the answer to this because I've talked to you guys before. You guys actually went to the gaming industry because there's a lot of people working in gaming and they create incredible worlds
Right.
that all have physics involved in it.
Mm-hmm.
So you just went there, right? And said,
Yeah.
why don't we just use what already exists?
Why reinvent the wheel? There's decades of development happening there. And so, and maybe the one thing I like to think about is like, remember we used to play these 8-bit games back in the day, right? Really pixelated or 2D.
Yeah.
And then like the first 3D games came along and they're really low poly. It's like blocky but fun, right? It's like you got a sense of motion. I remember playing. This is a 2D game, but playing Prince of Persia back in the day. I don't know if you're.
Oh yeah.
They like rotoscoped the capture of the player, and it was so lifelike, even though it was just pixels, right? And then fast forward to like today, where you can look at a game and it looks just like it's photorealistic, and then introduce like GANs into that, and really had this like super like indistinguishable from the real world. I think the same thing, we're going to start to see the same thing in this mirror world approach, is where today the sensor data is not that great. You can sort of see where things are. It's low poly, but we can get lots of value out of it, like with autonomous cars or factories or retail or whatever. But with Moore's law, with better sensing and better compute, the fidelity of that twin and the additional use cases that will come along to that will drive this virtuous cycle of better sensing, better compute, better twins, more value, back to being able to invest, and it'll be this massive virtuous cycle that will drive this technology forward.
So Rob, do you think that the gaming industry, then the standards that they use, are they sufficient enough to model the real world, or they're missing things in there that you need to add to it, or can you take it for just as it is?
Well, that's a really good question. I think that we should try to use as much as we can, but typically, like a renderer works on a frame-wise basis. So it's
Right.
sort of like, a clock.
It's taking slices in time, right?
It's like just rendering forward. With the real world, it's a little messier. You might have really asynchronous, like some low latency, some high latency. sources of data that are all coming in at different time scales and everything. And you need to be able to coordinate all of that and sort of bring in the accuracy of these things, or the error bars in, and be able to make sense of that, model it, and maybe do some things like say, well, how latent is something? How much time do I have to get the data in into my model? Maybe I can model with less. I can run my understanding of the world near real time at relatively low fidelity. It's a little chunky, but I can store all of that data and render it in higher fidelity, for historical analytics. So it's definitely messier, but we're standing on the shoulders of giants here. I mean, a lot of the work that's there in the gaming industry can be reused for sure.
Oh, that's awesome. So my next question is the product that Intel has, it's called SceneScape, right? Something you've been working on for some time. This is not like new stuff. This is not, oh, Rob did this in his basement with a couple other pals at Intel. Tell me, I mean, is this a product that people can look at right now? Can they? And then what use cases are you guys using it for today?
Yeah, well, it kind of did start as something that we developed on nights and weekends. It was like a vision. It really did come around saying, how do we get from pixel-based units into real-world units, like in cameras? And we quickly realized that if we can separate things out into the multimodal tracker along with, motion modeling and everything, now we can support other modalities and we can make things better. But yes, Intel SceneScape is the result of that work, and hopefully, with our customers and our partners, we can drive this vision forward to really improve outcomes for our customers. And in terms of use cases, really, it sort of started out in cities and transportation, like being able to make sense of what's happening on roadside cameras, or say, how do I track cars from one camera to another or whatever. But we quickly realized that tracker use case, the multimodal tracking, is a sort of needed capability across industries. So it quickly extended into things like healthcare, for example. Imagine a scenario where you could track where the instruments are in an operating room, to make sure
So
that
nothing gets left in someone's body, maybe?
If I track something going into the patient, I need to make sure I'm tracking it out, for example. That's a high fidelity use case that requires lots of high resolution cameras to do, and 3D detection and all of that. But really, it's the same problem as tracking a person moving in a factory and making sure that I don't turn on a robot when that person is nearby or whatever. So these are safety use cases, but I think there are some other use cases, like just to improve operational efficiencies that we can do sooner, like, or just knowing how many people are in line at the store, or knowing if I need to turn the lights on using a common digital twin rather than special purpose sensors.
So I find this interesting because you talked about multimodalities, and one of the demos that you guys have shown me is you can estimate where someone's going to go,
Mm-hmm.
and the next camera that they should be showing up in. And when they don't, then, because a lot of times you can't cover your whole space with cameras or sensors, but where the gaps are because you have a 3D model of it.
Mm-hmm.
And when someone's walking and following a path, where they are in the factory.
That's the idea, and it's another really interesting aspect of this is that no two sensors agree on where something is.
Interesting.
Right? It's like there's always some error bars. Back to the physics thing, there's always an error bar on that measurement, right? And so if I have cameras that overlap or other sensor modalities that cover the same area, I need to be able to reconcile the measurement about where somebody is. And then if I can set up a motion model, I say, well, here's the mass, here's the velocity, here's the maximum acceleration, that's back to physics, right? It all comes down to physics. The maximum acceleration that this thing can handle or perform, then I can set up and do some extrapolation. I can say, yeah, this person is moving in this direction, and it's probably the same person we saw previously if they showed up in the next camera if I don't have coverage in that area, or a measurement of the track. So yeah, I mean, the physics definitely comes into it.
So, a lot of people that think about digital twin, they say, just put cameras up and you'll know everything. Rob, thanks for explaining it. It's a complex problem. It's not easy.
Yeah. And think about the fact that it's a continuum. It's like you have low latency digital twins for real time type stuff, and higher latency ones like Google Maps that for longer term historical stuff. But really, in the end, it's all going to sort of compress into the real time and really improve outcomes for a lot of, I hope that like a lot of technologists, I hope that we can use this technology responsibly and really improve outcomes for ourselves and for our
the use cases, my mind's just going crazy on use cases right now, mostly tracking my children, but that's
Is that truly a responsible use? I'm not sure, Darren.
That's a totally responsible use. Right. As a parent, yeah, it's totally responsible.
I love it.
All right, Rob, hey, thanks for coming on the show today.
Of course, Darren. Take care.
Thank you for listening to Embracing Digital Transformation today. If you enjoyed our podcast, give it 5 stars on your favorite podcasting site or YouTube channel. You can find out more information about Embracing Digital Transformation at embracingdigital.org. Until next time, go out and do something wonderful.